DeepSeek V3R1 versus Kimi K2, Architecture and Performance Analysis. A tale of two AI philosophies, more heads versus more experts. The Great Architectural Divide. In the rapidly evolving world of large language models, two distinct philosophies have emerged, beautifully illustrated by DeepSeek V3R1 and Kimi K2. These models represent fundamentally different approaches to achieving AI intelligence, each with unique trade-offs and optimization strategies. DeepSeek V3R1, the multi-hat approach. Philosophy, more heads, fewer experts. DeepSeek V3R1 embraces a distributed attention strategy, spreading computational load across numerous attention heads while maintaining a more streamlined expert system. Key architectural features: massive vocabulary foundation. Vocabulary size 129K tokens, nearly double that of Kimi K2. This extensive vocabulary enables more nuanced understanding of diverse languages and technical terminology. It reduces the need for subword tokenization, leading to more efficient processing. Multi-head attention strategy. 128 attention heads in the core architecture. Each head can focus on different aspects of the input simultaneously. It creates rich parallel processing pathways for complex reasoning tasks. Streamlined expert system. Mixture of experts layer with selective activation. Only 8 experts active per token. Highly efficient resource utilization. 575 total parameters active during inference, despite the model's large size. Extended context window. Supported context length 128K tokens. Enables processing of extremely long documents, conversations, and complex reasoning chains, perfect for applications requiring extensive context retention. Resource efficiency. Model size 671B parameters with selective activation, 575 parameters active per inference step, remarkable efficiency. Optimized for both performance and computational cost. Kimi K2, the expert-heavy approach. Philosophy. Fewer heads, more experts. Kimi K2 takes the opposite approach, concentrating on a sophisticated expert system while maintaining focused attention mechanisms. Key architectural features: focused vocabulary. Vocabulary size 160K tokens, optimized for specific use cases. Carefully curated for maximum relevance and efficiency. Reduces computational overhead while maintaining coverage. Concentrated attention. 64 attention heads, half of DeepSeek's count. Each head is more specialized and computationally intensive. It enables deeper, more focused analysis per attention mechanism. Expert-rich architecture. Mixture of experts with 8 experts active per token. 329 total parameters active during inference. More specialized expert knowledge per domain. Balanced context. Supported context length 128K tokens. Matches DeepSeek's capability. Identical context window enables fair performance comparison. Compact efficiency. Model size 1T parameters with selective activation. 329 parameters active per inference step. Ultra efficient. Smaller active parameter count than DeepSeek. Performance analysis where theory meets reality. The architectural differences translate into distinct performance profiles across different domains. Agentic and competitive coding performance. SWE bench verified results. This benchmark tests models' ability to solve real-world software engineering problems. DeepSeek V3R1 dominance. Kimi K2 71.6%, strong performance with expert-focused architecture. DeepSeek V3R1 65.8%, competitive but slightly behind. Other models trail significantly at 38.4%, 34.4%, and lower. DeepSeek V3R1 multilingual coding performance. Testing coding capabilities across different programming languages and contexts. Kimi K2 takes the lead. DeepSeek V3R1 47.3%, strong multilingual coding performance. Kimi K2 51.0%, superior multilingual optimization. Significant gap to competitors at 25.8%, 20.9%, and 31.5%. The architectural trade-offs explained. DeepSeek's multi-head advantage. Parallel processing. 128 attention heads enable simultaneous analysis of multiple aspects. Scalability. Architecture scales well with increased computational resources. Robustness. Distributed attention reduces single points of failure. Context utilization. Better at leveraging the full 128K token context. Kimi's expert specialization. Domain expertise, fewer more specialized experts per domain. Efficiency, lower active parameter count than 325 versus 575. Focused attention, 64 heads provide deeper, more concentrated analysis. Multilingual optimization, architecture particularly suited for cross-language tasks. Real-world implications, for developers, DeepSeek v3-R1 excels in complex, multifaceted coding problems requiring broad context. Kimi K2 shines in multilingual environments and specialized domain tasks. For enterprises, DeepSeek offers better scalability for diverse, high-complexity workloads. Kimi provides more efficient resource utilization for focused applications. For research, DeepSeek demonstrates the power of distributed attention mechanisms. Kimi proves that expert specialization can compete with brute force approaches. The bigger picture, evolution of AI architecture. These models represent two evolutionary paths in AI development. The scaling path, DeepSeek, more heads, larger vocabulary, distributed processing, betting on parallel computation and resource abundance. The efficiency path, Kimi, fewer heads, specialized experts, focused processing, betting on intelligent resource allocation and domain expertise. Both approaches have merit, and the performance results show that there's no single correct architecture. The future likely lies in hybrid approaches that combine the best of both philosophies, the parallel processing power of multi-head attention with the specialized intelligence of expert systems. Conclusion: different tools for different jobs. The DeepSeek v3-R1 versus Kimi K2 comparison illustrates that in AI, architectural diversity drives innovation. DeepSeek's more heads, fewer experts approach excels in broad, complex reasoning tasks, while Kimi's fewer heads, more expert strategy dominates in specialized, efficiency-critical applications. The performance benchmarks confirm that both approaches can achieve state-of-the-art results, but through fundamentally different computational strategies. This diversity in architectural thinking will continue to drive the next generation of AI breakthroughs, where the optimal solution depends not just on raw performance, but on the specific requirements of the task at hand.